The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. Sorry for the delay. There's been a little bit of hiccups. Could somebody please confirm whether you can hear me and see the screen at the same time in the chat box, please? Okay. Thank you very much, guys. Okay, so now we can begin. So thank you very much, guys, to join the second part of the webinar series. Now, this is probably the most important one, I think, because everybody probably would, well, I had when I did this, is how if the results are going to be accurate or not in SimSolid, especially when it's not using any mesh or any type of geometry simplification. So just for the very few people who couldn't join me in the first webinar, this is just a brief introduction about myself. I've been working for Symmetry for over 10 years. I have some several product experience within the simulation field, including ANSYS, which is heavily used within the design community, MSC, Algo, which was SimMechanical when it was purchased by Autodesk, and latterly it was called Autodesk Simulation, and obviously I present at the Autodesk University events around the world. So very briefly, just want to, now I'll try to decide how I was going to compare the results. Now in my following session next week, I will take Nastran in CAD or Inventor Nastran as an example to compare the results, but in this case here I'm going to use some theoretical results and also NAFEMS, which is the independent FEA body around the which people use to determine whether the results are being more accurate compared to some sort of standard test. And then we'll go through how to access SimSolid if you have not done so already, and hopefully some time for Q&A. Okay, just double check if there's any questions very quickly. Okay. Okay, so the first example is a standard theoretical example. Probably, I mean, I came across it when I was at university, is to take a plate with a hole and apply a tensile load at either ends. Now I've got a link here. So this is basically fracture mechanics. If I just go scroll down a little bit, you probably see it. There we go. So this is where I've taken the data from, and we're going to basically compare this result. Now, typically, if you were to analyze this in Inventor FEA or even Nastran, for example, we would try to do it as a quarter model, but because we're using SimSolid, I'm going to show you how to do it as a whole complete plate with loading applied at either end. So let's have a quick look. Okay, so let's open the file. Again, it's a step file, so I've got a plate with a hole. And let's have a look at some of the views. And then we should rotate it by 90 degrees. Now what I'm doing here, I'm showing you how you can actually do saved views. So we can save the view here, call it view 1. Right, so first of all, I'm going to define the material. And now we're going to choose a linear analysis. And the loading we're going to apply on this is a pressure. and it's 100. Now, so that it's being compressed, so I need to change the loading to negative. And if I was to run this in Inventor as an example, or Nastran, it will probably fail, saying that it needs extra constraints. So let's just check here. So we've got the same thing here. So what I'm going to do here is there's a special constraint here called inertia relief. So if you apply that, once it tries to run, it applies forces in the opposite directions to create some sort of steady state. And one more thing I'm going to do here before we run this, I'm going to change the settings to stress just to give more accurate results. Now let's run this and let's see what type of result we get. Okay, that was pretty quick. So I'm going to look at the tensile major principal stresses, and we have a value of 368 megapascals. If I go back to my presentation, so taking the value of 368 gives us a stress result difference of less than 1%. So this is a simple example to compare the results. Let's just take another example now. Now, these are well-published tests by NAFEMS. And what I've chosen here is not all of them. I've taken a handful of these tests, which I'm going to go through and show you what type of results we get when we compare these against NAFEMS. So let's take the first one, the elliptical membrane. So this is the example, and we're going to apply a 10 megapascals. We're going to model this as a symmetrical model. We've got pressure on the outside elliptical shape. We're going to define symmetry conditions and then determine if we get similar stresses to this benchmark test. Okay. Okay, one of the things I like about SimSolid, I don't need to open a new analysis. I can actually use the same analysis and bring in a completely different part. So I'm going to go in here and bring in the elliptical plate. And what it tries to do, it tries to map as much data as possible. Now, because the geometry is completely different, it's lost the pressure. So we're just going to reassign the pressure again on this outside surface. Okay, let's try it again. -10. And we're going to remove the inertia relief because we're going to fully constrain this using symmetry conditions. So we got something called frictionless constraints inside SimSolid. It refers to as slider support. So we'll click on that. Okay, let's just this one here. And then I'm just going to check the if everything's okay. Okay, material has not been assigned, so let's assign the material. We still have this, it's not been fully restrained because it can go and move in the Z directions, but I don't want to restrain in the Z directions. So what I'm going to do here is I'm going to apply a small, like a spring constraint, or allow it, I'm going to pick a point to stop it moving in the Z direction so that the analysis can proceed. So I'm not going to fully restrain it because that'll be incorrect. So I'm going to go in here and pick a node on anywhere on the geometry. I'm going to decide to pick it here and saying that it can't move in the Z direction. And now hopefully we should be able to run that. Okay, and then we need to look at the stress Y in this. That's what we're comparing. And if I hide the boundary conditions, if I zoom in, if I click on the max, now that max value is in the middle, so I want to pick the value on the corner per the test. Okay, so we'll click on the probe here, zoom in a little bit, and we've got a value around 92.7 megapascals. So if we go back to our power presentation, and there we go again. So we have a very, very similar value, almost very little difference between the results. So here is less, it's almost 0%. So let's try something different. Okay, in this case here, we're going to use a skewed plate. So this is a classical example where we have deformed elements in classical FEA products like Inventor Nastran, because SimSolid doesn't use elements. So we're going to see what type of results we're going to get inside SimSolid. So we're going to apply a pressure of 0.007 megapascals and see if we can get 0.82 megapascal results. So let's try this. So let's close this one again. I'm going to continue with the same project and click on the skewed plate step file again. Okay, I want to see the edges. Okay, because we need to determine the stress at this point here. It's simply supporters, so we can't actually fix it at the ends. So if I zoom in, let's just apply the metal steel first of all, assign materials. And let's assign the pressure. It's 0.007 megapascals. Now, the trouble here now is these edges, if I pick these edges, it's going to completely fix it, which means it'll give me a huge amount of stress around the perimeter. So we're basically going to apply simply supported, and the way we can do this is if I use this force displacement. It's a bit like in force displacements like you do inside Inventor using the constraints. So if I go to edge, I'm going to stop this plate moving in the Z direction. The reason why these are not highlighted is because I need to remove the inertia relief. So let's do that first and then try it again. Pick edges, and now we go and pick the edges. Okay, so pick the 4 edges. Now these 4 edges, we need to restrain it in the Z direction. So if I go to Z here, so these edges will not move in the Z direction. But also I need to stop it going in the Y and X. So what we'll do here is we'll pick the points. So first of all, let's pick that point there. This is to give it, and we need to stop that in the Y direction. So put that back. And just this one here in the X direction. This is to give it stability in the model. My other option was to use the inertial relief, but I wanted to show you a different alternative way of doing it. So this is X, and if I just press OK, let's look at the view, and let's check it again. And we still have free body motion. So what I'm going to do here is I'm going to take the last one and add another point on the opposite side. This one here. And let's try and run this. Okay. And Now I forgot which one it was, so just give me 2 ticks. It's the mass principal stress, okay. Before we do that, let's try. Okay, now we get high stress on the corners, but that's the same we get in the NAFEMS. But I'm interested in the middle, so I'm going to zoom in here and use the probe, and we get about 0.823. So there we go again. So we still have, well, in this case here, we get about 2.2% potential difference between the results because of its skew plate, but which is acceptable. In the industry, normally use a value of 10%, but obviously the smaller the value difference, the better it is. So that's slightly higher than the previous 2 tests, but still acceptable. And let's go for our final test. Now this is a hemisphere example, and we're basically going to pressurize it. Now typically when we're doing pressure vessels or spherical shapes, we normally use it as a quarter model or do it as a 1/8 of a model for stability. But in this example here, I'm going to take the whole shape and try to use inertial relief to be able to determine the results. So let's just go through that process. Well, let's try one more. So I'm going to use the tank full. It looks like it, when it's opening, it looks like a capsule. Okay, right. So I've done this on purpose because obviously this creates lots of problems using in Inventor and possibly in Nastran without actually adding any extra stability constraints. So I'm going to try and do it in here. So we have the inertial relief already on. Now the only snag is now I need to apply pressure internally. So I'm going to try and use some of these clipping planes. Okay. So if I go into here and add tangent faces, and I'm going to pick inside one face, and it picks everything, and it's 1 megapascals. And I can then move my slide plane away. Let's see. Okay, so pressure applied looks correct. So I'll remove the clipping plane. And before I forget, because we're bringing as a step file, we need to assign the materials again. Okay, so we've got pressure, initial relief. Now we should be able to run this without any extra stability constraints like the previous examples. So this is going to take a little bit longer. Hope not too long. While that's running, I'm just going to have a look at some questions. So what it's doing now is going through all the convergence process. This is automatic in SimSolid, so it goes through automatic convergence. And when you are comparing results for stress, it goes through 5 iterations. So not just running one analysis, it's going through 5. Okay, let's just Typically, something like this, you would run it as a quarter model or 1/8 in Inventor and Nastran. And even the test sort of suggests that you use it as a quarter model or a half. But I'm just want to show you what type of results we get with this inertial relief. So I think we're at the 4th pass. Just got one more after this. Okay, we're almost done. Okay, so the results we need to look at is the axial stresses down the Z direction. Okay, so what I'm going to do here is I'm going to find the maximum stress. So we're going to go in here and just specify a value of 25. Let's spin it around and see if we got any help. There we go. So you got a red spot here. So let's try and make it smaller. And now I can use the probe and click somewhere in that region. We've got 25.693. So if I go back to my PowerPoint, and using 25.7, we have almost 0.6% difference in the results. Now, if you were to use this because of time, and I'm just not going to use the quarter model, and this is what type of results you will get with the quarter model, yeah. And it's slightly higher. It's about 3% difference in results. So both results are acceptable. You can do it either way. I mean, if you want me to show you the quarter model, let me just try that very quickly. If I go to my tan quarter, so the first thing we do here is remove the inertial relief and assign pressure. Oh, we need to put a value first of all. 1 megapascal. And the other thing we need to do here is put symmetry conditions, similar to what you would do in Inventor Nastran. Just one more. And we need to assign the material. And I think we're ready to run. Yes. So this should be a lot quicker to run. Okay, let's just, if I click on my idea, so if I'm just going to go and pick it this time, I should have a split line here somewhere to just show the distance on the outside surface. .1. Okay, so we go back to. So there we go, 25.1. So that just to give you an idea, two different results. Both results are acceptable. Okay, so it's just almost finishing off now. So if you want to try these are the documents. So we got one on the benchmark. This was done by NAFEMS. The Skewed plate was done by NAFEMS in January, just to demonstrate the results. This is the Altair verification manual, and all the tests are comparisons against SolidWorks. And this is the old document from Autodesk and NAFEMS, which you can access, and the examples I have chosen are from this document, and you'll also see the Inventor results and the old Sim Mechanical as well. And if you haven't downloaded the software, I suggest you take it for a spin. You have up to, I think, 60 days, I'm not sure if it's 90 days, to allow you to sort of try it out and actually make your own decisions on what you think of the software. And per our first session, you have full support. There is numerous amounts of documentation for you to download as soon as you register for the trial. You can actually, and then we have your phone support with ourselves and remote meetings. And also you can attend the one-day SimSolid courses run by Altair, and are hoping to continue these webinars over the coming weeks. I hope you guys can join me next week, where I will take Inventor Nastran and SimSolid to compare the results, show you the differences in the workflows, hopefully on time this time. And now if you've got any questions, and these are also showing the list of forthcoming webinars. Okay, so we've got some questions here. The session, yes, it's being recorded. You will get a link in the next couple of days. The next question here is, what is the alternative for inertia relief in Inventor stress? There is no alternative, but I think for single parts there is an option where you can switch on rigid body modes. But you've got to be careful that if you don't get a high stress, because what rigid body mode does in Inventor, it creates small springs or weak springs, which can result in high stresses if the spring becomes a strong spring. But you can try it, but that's what it means. It's rigid body modes in your stress settings. And the next question is, how does SimSolid handle assemblies? Fortunately, the next webinars will be all assemblies, and the SimSolid strength is assemblies. One of the things which we aim to promote SimSolid is at large scale assemblies, and it's very fast. But hopefully you'll see that in the forthcoming webinars. Okay, I'm just going to hang fire for any more questions you may have. Okay, well, thank you very much, guys, for attending this webinar. I hope you can join me next week. And thank you very much. And don't forget to download the trial. Bye for now.